Last time we derived quadratic equations from 3 points. So we created a system of equations in order to write that equation. Today we're going to go ahead and focus on all the other different ways that we can write a quadratic equation. And so to do that, we're going to start by talking about the quadratic parent function. And so our quadratic parent function is f of x equals x squared. Let's think about some of the points that would go in there. So if I plugged in 0, 0 squared is 0. If I plugged in negative 1 squared is positive 1 because negative 1 times negative 1 gives you a positive. Negative 2 squared would be 4 because negative 2 times negative 2 is positive 4. 1 squared is 1 and 2 squared is 4. So from this table of values, you can see the symmetry around this 0, 0. When we graph it, we'll see those points as well. 0, 0, 1, 1, 2, 4. If you kept going, you would find 3, 9, and negative 3, 9, as it gets squared to go on both sides. So it makes this U shape right here. This is our quadratic parent function, y equals x squared. That parent function can be transformed. So one of the equations that we will see is an equation of a quadratic that's been transformed with our a, b, c, and d. When we talked about absolute values, we talked about how these transformations work. They are no different with quadratics. They work exactly the same. In fact, with all of the functions we deal with all year, the only thing that changes is the operation. So here we see the squared from the parent function, x squared, instead of our absolute value bars. But everything in this equation is going to work exactly the way it did with the absolute values. So when a is between 0 and 1, it is a vertical compression. When a is bigger than 1, it is a vertical stretch by a. So the scale factor is that a value. When it is negative, it is a reflection across the x-axis. Now for the b values on the inside, and so these all affect the y values. So when we're trying to graph these or write the equations, we know those affect the y values because they're vertical. Inside of our operation, these things are going to affect our x values. And so it is going to be horizontal transformations. And so when b is between 0 and 1, it is a horizontal stretch by 1 over b. When b is greater than 1, it is a horizontal compression by 1 over b. And so that doesn't look right because here you said between 0 and 1, it was a vertical compression. Here we're saying when it's between 0 and 1, it's a horizontal stretch. So these look like they flipped. But if you look at that scale factor, that's the reason. So if inside the equation here, it was a 1/2, the scale factor would be 2. And so our scale factor would look just like this right here, the stretch. So keep that in mind. Now, when it is negative, it is a reflection across the y. You won't see much of a difference with that one since it is symmetrical. Our axis of symmetry cuts right through here at 0. I'll go ahead and write that here just so we have it. Axis of symmetry is at x equals 0. It is our y-axis. That means that I can fold it right there, and this side would land right on top of this one. So if we have a reflection across the y, then this side would land right on top of this one, so you don't really see a difference on the graph. The other horizontal transformation, again, inside the operation, those are always the horizontal ones, is our right and left movement. And so if it is x minus c, it is going to go to the right c. And if it is x plus c, it's going to go to the left c. And then for our d value, that's up and down. So knowing these transformations is crucial really for the whole year's work that we're going to do with all the different functions, and then again in your following math classes. But you want to know these transformations. It helps you with graphing and it helps you with writing equations. So we're going to look at these three graphs down here, and we're going to use what we know from the equation to write the equation of the quadratic. That is one way of writing it, from transformations. So when I look at this one right here, we know that the parent function has its vertex at 0, 0. And then it's got the point 1, 1 and 2, 4. And the points that are symmetrical to that, giving you that shape right there. So looking at this graph, I can see a couple of obvious transformations. I can see this has moved to the left. I can see it has moved down. So now I know those transformations for sure. So I look at my vertex here. I look at my vertex on the new one. It has moved to the left 3 and down 8. So down 8, left 3. Now, when I check the next point over, we see it goes over 1, up 1, and over 2, up 4. Over 1, up 1 would be right here, and over 2, up 4 would be right here. So now we know there is another transformation there. There is a stretch. It looks like we took this right here and pulled up so that instead of here, it has gone here, and instead of at the 2, 4, it is at the 2, 8. That tells me I've doubled my y values. And so I have a vertical stretch of 2. And so now we can write the equation. We work backwards from these transformations to write the equation. So my equation would be y equals 2, because that's my vertical stretch, x plus 3 squared, because this right here tells me to go to the left 3. This tells me I started with the quadratic parent function. And then down 8. All right, let's try another one. So here is my key points for my quadratic. Just going to draw them there so that you can see what it looks like and start thinking about those transformations. Again, we've got some obvious ones. I can see instead of moving upwards, it is going downwards. So we have a reflection across the x. Because instead of being concave up, opening upward this way, it is concave down, opening downward. I can also see that it has moved to the left 2 and down 4. Now we check any other points. So my vertex, left 2, down 4 is right there. We said it's got a reflection, so these 2 points should go over 1 and down 1 and over 1, down 1. Those are right there on my graph. If I check the next one, 2, 1, 2, 3, 4, all of those points are in the correct location, so I know I have no reflection. I'm sorry, no stretch, no compression. And so my equation would be y equals a negative, because that's what causes the reflection across the x-axis, x plus 2, because that makes it go left 2, and then minus 4 is the down 4. All right, if you want to try one, go ahead and pause the video and try this next one there, and see if you can do it correctly. I'll go ahead and continue with it here. All right, so our parent function starts at 0, 0. This moves to the right 3 and up 1. So I'm going to go ahead and write those down. Right 3, down 1. The next point I check is 1 over and 1 up. Well, that's not on my graph, so I know that's a stretch or a compression. I'm going to check the next point over. When you go over 2, it should be up 4. 1, 2, 3, 4. Again, not on my graph, so we know there's a transformation here. All right, so it's time to look at what is that transformation. So it's supposed to be over 1, up 1, but it's not. It's over 1 and just a little bit here, not a full 1. And then it's supposed to go over 2 and up 4, but it is over 2 and up 2. So 4, but it's at 2, 1, but it's at about a half. So this has been vertically compressed. It looks like we took it from the top and we squeezed down. So this point went down here and this one came down here to 2. That's a vertical compression. And you could see it best at the 4. So it was supposed to be 4, but it is 2. So we have vertically compressed it by 1/2. It is a half of what it's supposed to be. All right, so we write our equation. A vertical compression by 1/2 tells you to put the 1/2 in the place of A on the front. And then right 3 is a -3 on the inside of the operation. And then down 1 is a -1 at the end. So by knowing the transformations, I am able to write the equation of the quadratic. All right, let's talk about the 3 forms that there is of the quadratic, because last time we saw the ax squared plus bx plus c when we use the calculator or a system of equations to write that. That's called the standard form. The equation that we were just working with is the transformational form. It's also the vertex form for the quadratic without the b part here. So a times x minus h squared plus k is considered the vertex form. And then there's one other form, the factored form. That's a times x minus r1 and x minus r2. This is the factored form. So a quadratic could be written in any one of those 3 forms, and you can actually move from one form to the other depending on what information you want. So in order to look at this top one, the standard form, let's talk about a couple. When we were working on that system of equations, and we saw this here, we did talk about that the c value is the y-intercept. So the standard form gives us our y-intercept. Let's think about that. Our y-intercept is when x is 0. So if I plugged in 0 here and here, then all of this would go away. And so there is my y-intercept of c. All right, the other information it gives you is this a value right here. If my a value is greater than 0, it's positive, then I know that the quadratic is concave up. It's going to open upward. If it is less than 0, so negative, then it is going to be concave down. There's one other thing you can get from this. That's that axis of symmetry. So an axis of symmetry, it's vertical for quadratic, so we know it's going to be x equals, and if you do negative b over 2a, that is the axis of symmetry. That's going to be this line right in the middle here that breaks our quadratic in half. And so that's the vertical line, and it's negative b over 2a. That's really all the information we get from the standard form. It doesn't really help for graphing it completely because you can't just graph with this information. It doesn't give us as much information as the others. So we will be using that vertex and factored form a little bit more. The vertex form, guess what it gives you? It gives you the vertex. The vertex is h comma k. So it's this value and this one. Now notice this is a minus here, so you want to be careful when you take out the vertex. If it said x minus 2, then the x value of the vertex is just the 2 because the minus is part of the equation. It also gives you that the concavity, so if a is greater than 0, it's also concave up. If it is less than 0, it is concave down, so we still get that same information as the standard one. It also gives you all the transformations. So you're able to write or graph the equation with that. The left and right movement, the up and down movement. So you could graph that from that equation. All right, our next one here, our factored form, gives you the roots, which you also know as x-intercepts or solutions. They'll be called several different things, but these right here are our roots. And so we would write that as r1, comma 0 and r2, comma 0. Because roots, x-intercepts, that's where it crosses the x-axis. And so we know that the y value there is 0. So we write that as an ordered pair with a 0. So this would be my first root. Again, notice that there's minus signs there. So if this was x minus 2, then my root would be 2. If it was x plus 2, then my root would be negative 2. So that gives us our x-intercepts. It also gives us the concavity. Again, if a value is greater than 0, it's concave up. If it is less than 0, it's going to be concave down. You could also get the axis of symmetry from this one. It would be x equals the first root plus the second root divided by 2. That's just the midpoint formula. Basically, you're going to take those two roots and find the center value, and that's going to give you the axis of symmetry. So those are the three forms of the quadratic. We're going to use them quite a bit. So let's keep going with the information it gives us. It says you can write a unique quadratic function given a vertex and a point on the parabola. And so here we put the notes on there so you can see exactly the way it is. We're going to go ahead and do these two together. It says write the equation of the quadratic given the vertex and a point. So with the system of equations, you needed 3 points in order to write the equation of a quadratic. If you have the vertex, all you need is one other point. So you can write that equation a little bit easier if you have that information. So let's try that. It gives us a vertex and a point, and so we want to use the vertex form, which is y equals a times x minus h squared plus k. And so we start by plugging in our vertex. We said that was h comma k. So h is going to be 3, k is going to be negative 4. And so we have that right there. Now, the reason why they give you another point is because we know every point came from this equation. So every point on the quadratic came from this equation, from this quadratic. So this ordered pair had to come from here. And so we now have an x and a y value. So if we plug in that x and that y, we're able to solve for the a. So I'm going to plug in 4 for my y and 5 for my x. And now we're going to solve. And so the math on this isn't crazy difficult. 5 minus 3 is 2, squared is 4. Don't change the sign. Minus 4. We are solving for this a, so I need to bring this on over to the other side. So I'm going to add 4, and I get 8 is equal to 4a. I divide by 4, and so a is 2. So my equation would be y equals 2x minus 3 squared minus 4. We have now written the equation in the vertex form. All right, let's try another one. Same thing, we've got a vertex, we've got a point. I start by putting in my vertex, so I get x minus a negative 1 squared plus 5. So I've plugged this in for h and 5 in for k. So negative 1 for h, 5 for k, because the vertex is h comma k. All right, when we have a minus and a negative, those two signs cancel, so it turns into a plus. Now we're going to use the other point to plug it in. So we get negative 4 is equal to a times 2 plus 1 squared plus 5. I subtract the 5 to get it to the other side. 2 plus 1 is 3 squared. So negative 9 is equal to 9a. 3 squared is 9. I divide by 9, and my a value is negative 1. So my equation is negative x plus 1 squared plus 5. We have written the equation from a vertex and a point. Notice this is also the transformational form, so you can say this had a reflection across the x-axis. It went to the left 1 and up 5, so that helps you with that as well. You've got 2 to try down here. Go ahead and pause the video, try the 2, and see if you've got the correct answer. All right, check your work. See if you got the correct answer. You should have solved for a and got 1/2 on 3, and then we're able to write the equation. On 4, you should have been able to solve for a and got negative 3 and wrote the equation. All right, let's continue to write more quadratic equations. All right, we're going to try another form here just by putting it in a word problem. So it's still a vertex and a point, but we're going to go ahead and put it in a word problem so you can see how that goes. The amazing Larry is a human cannonball. He would like to reach a maximum height of 30 feet during his next launch. Based on Amazing Larry's previous launches, his assistant Dewan has estimated that this will occur when he is 40 feet from the cannon. When Amazing Larry is shot from the cannon, he is 10 feet above the ground. Write an equation to represent Amazing Larry's height in terms of his distance. All right, so he is being shot out of this cannon right here. There he is. All right, it says he is 10 feet above the ground. So we know this part right here is 10 feet. Now, it says that he is going to reach a maximum height of 30 feet during his next launch. And that will occur when he's 40 feet from the cannon. So he's going to go up, and then we know gravity's going to take him back down, so he's going to come back down. So this is what we've got. It says that when he is 40 feet from the cannon, so 40 feet this way, he's going to be at his maximum height right here of 30. So that would be 40, 30. That's our point. That's our vertex. The maximum height is the vertex of a quadratic. So we then have a vertex here. We also have this point right here because he told us it was 10 feet from the ground, and that is 0 feet from the cannon. So we know that point is 0, 10. So we also have the y-intercept. Now, with the y-intercept alone, you cannot write the standard form. So we can't use that one. Now you can remember that there is symmetry in quadratics. And so if I know this point 0, 10, then it went 40, then I know another 40, it has to be at the same point. So I know this has to be 80, 10. So I technically have three points. I can do the system of equations and solve that way. But this one's so much easier to do as a vertex form since I have the vertex. So my vertex is 40, 30. So that would be x minus 40 squared plus 30. That's my h, that's my k. Now all I have to do is solve for this a. I can choose either one of these points because every point on this quadratic came from this equation. So any point on the quadratic works. I'm going to use this one just because it's probably going to be easier. So I plug in 10 for my y, 0 for my x, and now it's time to simplify this. So I'm going to subtract the 30 to get it to the other side. So that gives me negative 20 is equal to a. Negative 40 squared is 1600. Now we divide by 1600. And we can reduce that negative 2 over 160 to be negative 1 over 80. So there is my a value, and my equation would be y equals negative 1 over 80 times x minus 40 squared plus 30. We wrote the equation for Amazing Larry's human cannonball shot. All right. You can convert from one equation to the other. Now, converting it from the vertex form to the standard form is the way you guys are used to from Algebra 1. You would FOIL this out and then distribute, and so it'd be in the standard form. The hardest one to convert from is from the standard form to the vertex form. So we're going to try that one first here. We do that by something called completing the square. So they gave it to us in this standard form. We want to convert it to this vertex form, and we do that by something called completing the square. This right here is considered a perfect square, x minus h squared. So in order to get it to look like that, I need a perfect square trinomial that will factor to be that, and then we can get it into the vertex form. So what we do is we complete our square with this equation by adding a missing term here that would make this a perfect square trinomial that factors to look like this. The minus 7 will be over there at the end. Now, I can't just change the value of this equation, and if I add something right here, I'm changing the value of the equation. So I need to subtract whatever that is here at the end. Because if I added and subtracted, that would be 0. I'm not changing the value of the equation. All right, to make this a perfect square trinomial, we take this middle term, divide it by 2, and then square it. So 6 divided by 2 is 3, squared is 9. Whatever I do there, I have to subtract it because plus 9 minus 9 is 0. So I have not changed the value of this equation. I've just changed the way it looks. And here's the reason why we did that. I need to factor this now. And so remember when we factor, we can go into x times x here. We're looking for what multiplies to be 9 and adds to be 6. Well, that's 3 and 3. Notice they're the same. This is a perfect square trinomial. It's always going to be the same factors. That's why we find this missing term right here with what we did, is because they'll be the same every single time. Minus the 16, which we actually write as x plus 3 squared minus 16. So now it is in the vertex form. I know that was a lot. Let's try it again. All right. I'm looking for my missing term. So I'm going to add something here to make this a perfect square trinomial. Whatever I add, I'm going to subtract from the end so that I'm not changing the value. So right here, we take this middle term, divide it by 2. So negative 10 divided by 2 is negative 5. And then I square it. Negative 5 squared is 25. If I add 25, I subtract 25. Now we factor. We said it's going to factor to be the same factor, so I can go straight into my parentheses this way. And actually, it's always going to be this middle term divided by 2. Negative 10 divided by 2 is negative 5. If you don't believe me, try it the other way. What multiplies to be 25 and adds to be negative 10? That's negative 5 and negative 5. Now, 22 minus 25 is negative 3, and so it is in the vertex form. All right, these are a little bit harder because the x squared is not by itself. So the first thing I need to do is factor that out. So I'm going to factor out a 2 here. Now, 2 times x squared is 2x squared. 2 times negative 10x would give me this negative 20x. Then I have my missing term and my 52 out here. All right. Now when I add my missing term here, I'm not just adding that, I'm adding it times 2 because the parentheses, if I distribute this, the 2 would be multiplied times this. I need to take that into consideration when I do that here. I need to also subtract 2 times that because you've got to subtract the same exact amount so you're not changing the value of the equation. Other than that, everything works pretty much the same. So I take my middle term, divide by 2. So negative 10 divided by 2 is negative 5. Squared is 25. And so I need to subtract 2 times 25 because here I'm adding 2 times 25. Here I need to subtract 2 times 25. Now I'm ready to factor. That's x minus 5 squared. Over here, I've got a 52 minus 50 because this is negative 2 times 25. And so my final answer is x minus 5 squared plus 2. All right, let's try that again. I factor out my negative 3. Remember, factoring is just undoing the distribution. So negative 3 times x squared gives me negative 3x squared. Negative 3 times negative 4x gives me that 12x. And then I need my missing term. Then I have the 22. Now over here, I had a negative 3 times this. So I'm actually subtracting. So I need to add a 3 times. We take the middle term, divide by 2. So negative 4 divided by 2 is negative 2. squared is a positive 4. So over here, we've just done negative 3 times 4, which is negative 12. Here we're doing a positive 12, so they undo each other. Now I'm ready to factor. So that's x minus 2 squared. 22 plus 12 gives me a 34. So I'm in my vertex form. This equation gives me my vertex, 2, 34. Remember, that's h and k for the vertex. So if they gave you an equation like this in standard form and they asked you for the vertex, you would need to convert it to the vertex form so you can pull the vertex out. All right, try the next two here and see if you can find the vertex form from that standard form. Go ahead and pause it and check your answers. All right, check those last two. You've got your two vertex forms there. You should have gotten x plus 3 squared minus 1 on this first one, and y equals 2 times x minus 2 squared plus 12 on the last one. All right, that was writing all kinds of quadratic equations.